Okay, so what we established is that in something that is suspended from a wire or a rope or a cable, it's got a gravitational force down on it, but if it's hanging out there in space and there's no surface to exert an upward force, the force that we have in that rope or cable or wire is called force of tension. I should be careful about using arrows in this chapter. So force of tension is really easy in a case like this. With all of these net force problems, and I realized this morning as I was getting ready, I thought, I'm not sure we made that explicitly clear. The place to start with these is always with a sum of forces on each axis. So we have sum of forces on the x, sum of forces on the y. And if they're not zero in each direction, then we're going to have a net force that's a resultant, and we can figure that out. You know how to do that. So here, for this particular object, is it, if we're told there's a box, 10 kilogram box, hanging on a cable. That's what it's doing. Somebody hung a 10 kilogram box on a cable. We don't know why, but they did. We could probably make really good use of the balconies in this stuff, huh? We could hang things over things. This will be great. So what's the sum of forces on the x? Zero. It's not moving left or right. Sum of forces on the x is 0. It's a really good idea as we go further in these for yourself, even if something's not moving on one axis, if it's not moving up or down or it's not moving left or right, it's still a good idea to do this sum of forces bit, because as we get into the heavier duty algebra, this gives you more tools with which to build expressions. So sometimes even though we aren't using what's going on one axis, it creates an expression for you to solve the axis we are working with. Okay, so sum of forces on this object, this box hanging on a cable, 0. Sum of forces on the y. Now, I don't know why physics students always chuckle when I say, well, they're equal to the force up plus the force down. And is this thing moving? No, it's just hanging there. So the force up plus the force down is equal to 0. Okay, I just got it. The first, I'll pause. Okay. So because the force up and the force down are equal to 0, what we know is that they're equal and opposite. This is a good place to start for you because, yeah, you know that that's force of gravity, and in this case, force of tension. If it was sitting on a tabletop, it would be normal force. But especially, as I said, as we get into more complicated problems, it gives you a handle to look at, okay, all the forces that are up on this object. Because it might not always just be normal force and force of tension. There may be things being pushed or whatever. The force down may not always just be force of gravity. There will end up being other forces down. And so that gives you a handle to then say, okay, what are all the forces that are acting upward on this object? For right now, it's really simple. What force is acting upward on a 10 kilogram box hanging on a cable? Force of tension. Yeah, that's the only up force we have. So force of tension we now know. And what's the down force on this box? Hanging on a cable. Force of gravity. So, oops, and I forgot something. Force of tension is equal to the negative of force of gravity. Now, that alone doesn't give us the necessary tools to solve it, because what we need to list is its mass. We've got a 10 kilogram box. We know that g is negative 9.81 meters per second squared. I'm going to shrink a few things here. Okay, so you know that the force of tension is equal to the negative of mass times gravity. So force of tension on this cable is equal to the negative of 10 kilograms times negative 9.81 meters per second squared. So the force of tension on this cable is equal to 98.1 newtons. That's really easy. Okay, so obviously since that was too easy, we need to make it harder. Okay, so now we've changed this up. And this is very much like what we've got on our parallelogram force board. Same 10 kilogram box that could be filled with, you know, whatever, cookies, Christmas tree ornaments, don't care. Something seasonally appropriate, a box of snow, oh wait, box of rain. So we got 2 cables on this thing now, and they're each making a 40-degree angle with the ceiling. So we could have these on eye hooks or whatever. So now we want to know, what is the force of tension in each cable? So let's shrink this. Place to start is always with sum of forces. So sum of forces on the x. It equals 0. But are there any forces on the x? Yes. Good answer, sir. There are. What are they?
The 2 strings pulling
Ah.
an angle.
These cables are not directly perpendicular to the horizon. They are not all on one axis. These strings are pulling on an angle, which means, and I'm going to draw this in a different color, for each string we have a force of tension on the y, and we also, and I'll draw this in another color, have a force of tension on the x. So this gets us into resolving vectors again. Now, the handy thing and the thing that's easy to forget when we're doing force problems, because we always show the force originating out of the center of the object. You go, ah, I don't know how to resolve that. The net force isn't here. What? I don't get it. Ah! Don't panic. Don't panic. Remember that you can always move vectors parallel to themselves. So we can bring this up here, and now we have a what?
Triangle.
A triangle!
It's all triangles.
It's all triangles. Actually, I realized the easier way to move it is probably to do, if I shrink, oh, hold on. If I shrink all this.
Put the Y on the other
Yeah, put the Y on the other side. So let's get that way up in the corner, and let's get the Y here. And that makes it much nicer. Okay, so why does that make it nicer? Because you get to use the angle you're given, not its complement. Okay, that's the critical piece. You're given, let me get rid of this, or at least move it out of the way.
It would be its complement, wouldn't it? Because you're not on the same side.
Well, hold on. Ah. Okay. Okay, so we were told that this was 40. This angle will also be 40. If you move the vectors, and you can do it either way. You can do it either way. I have a pea brain, and I try to avoid any opportunity for myself to make a really stupid mistake, like reversing my angles. This would allow you to not have to think about using 60 versus or 50 versus 40. So if you're using this angle, the force of so, okay, let's go back to this whole sum of forces idea. So sum of forces on the x we know is 0. What forces exist on the x? Okay. Force of tension on the x, 1, for cable 1, plus force of tension on the x, 2. Why is this important? Why does it matter?
Because they cancel each other out.
There's two strings. They cancel one another out, which gives us a piece of ammunition for later expression building. Yeah, we got our physics trajectories loaded. Okay, what that tells us is that force of tension x1 equals force of tension x2. Oh, negative thereof, sorry. What expression would we be using for force of tension on the x? Trig. Look back at the picture. Cosine. The force of tension on the x is the force of tension times the cosine of theta. So that what that allows us to do is say, well, force of tension 1 times cosine theta 1 is equal to the negative of force of tension 2 times cosine theta 2.
Should that be force of tension x2?
No, because I just put in the cosine. So yeah, it's. He was asking, should this be force of tension x? That's the expression for force of tension x. That force of tension times cosine theta. What this allows us to prove mathematically, so divide, we know that cosine, well, here's what we know. Whoops. We know that theta 1 equals theta 2. We were told that in the problem. So that allows us to now say force of tension 1 cosine theta 1 equals the negative force of tension 2, also of cosine theta 1. Well, now, divide both sides by cosine of theta 1. What do you get? That the forces of tension are equal. Okay. That seems like a ridiculously long, well, we already knew that. But when the algebra gets more complicated, having that tool that you've just built by doing the sum of forces on the axis that you feel like you're not using, so if we divide both sides by cosine theta 1, we end up saying, oh, well, force of tension 1 is equal to the negative of force of tension 2. Okay. Did you do proofs in geometry? Okay. This is, you know what, I had a guy for geometry in high school. We never did a single proof. I never did a geometric proof. And I have had multiple people tell me, oh, that's why you struggled in physics the first time through. Because having the geometric proof background really helps with the graphic nature of physics. So if you got hammered with proofs in geometry, it should serve you well in this. I cannot speak from personal experience because I literally have never done a geometric proof in my life. I keep begging somebody to show me how to do them. Yes, ma'am?
So even though we don't put the x, so we're still talking about the x-axis.
We're still talking about, well, no. What we've just done, so do you remember in the problems where like we have a golf ball, we have the total distance of its travel, and we want the maximum height. So we start off talking about just the point to maximum height, but then we build an expression for the whole travel. What we've done here is kind of the inverse of that. We've started off just talking about the x-axis, but from that what we've been able to prove mathematically is that those forces of tension are equal. So we've gone from talking about just one axis to talking about the problem in general. Okay, so now we're ready to deal with the axis that we really want. shrink all this. And this problem is not terribly difficult. I'm showing you all the steps. You could do this without doing that proof, but it's a tool that you need to have. So now let's talk about the sum of forces on the y-axis. As always, we have forces up, we have forces down. And this thing is not moving. Well, first of all, it's not moving, so sum of forces on the y equals what? 0. And we know that that's equal to all the forces up plus all the forces down. Okay, seems easy enough. So what that further means is that the forces up are equal to the negative of the forces down. I'm going to set some of this stuff aside. Shrink that even more, because we're going to need some space here. Okay, so what forces up do we have? Force of tension what? Force of tension y. Force of tension y what? Okay, I like it. So we have force of tension on the y, 1. Force of tension on the y for cable 1. What else do we have? Force of tension on the y, 2. F of t, y, 2. Any other forces up? No, we're done. We're done with F up. So, what did we say the force down on this was? Force of gravity, F of g. Okay. Are we ready to solve? No. So we have to do some more expression creation. I know. Everybody hates it. It's not just you. How would we express force of tension on the y? Going back to this picture. So let's get rid of that. And remember that the force of tension y is there opposite that 40-degree angle, sine. So force of tension on the y is going to be the force of tension in cable 1 times the sine of theta. And at this point I am going to kind of shortcut and I'm not going to go through the whole sine theta 1, sine theta 2, because we know that theta 1 and theta 2 are equal. We were told that in the problem. That will not always be the case. But in this problem, they're equal. So force of tension 1 times sine of theta plus force of tension 2 times sine of theta is equal to F of g. Well, what's... And I forgot to put in the negative of F of g. That was my fault. Okay, so force of tension 1 times sine theta plus force of tension 2 times sine theta equals force of gravity, which is equal to what? Mass gravity, mg. Okay. We are solving for force of tension. So we have a little bit of algebra to do. So the first thing we can do is say this. Well, force of tension 1 is equal to force of tension 2. So really, this is F of T1, and we could factor out a sine theta. Sine theta times F of T1 plus F of T1 equals mg. That factoring becomes really... Why would we do that?
No, I had a question, Ron. Wouldn't
Okay.
It's not negative?
It is negative. I'm sorry. I keep forgetting that. Can somebody throw something at me every time I forget to put in the negative? Sorry. Well, what we said... Thank you, Zach. I appreciate your volunteering spirit. We had said here that F of T1 equals F of T2. So we went ahead and substituted in F of T1 for F of T2. So if we factor out that sine theta, we have this. Well, can we start to isolate F of T1? I see crinkled brows, yes.
On the when we found
Mhm.
we had it the opposite. Which is-
Oh gosh, yes. Okay.
So then what do you think? So
Well, their magnitude is equal. Okay, hold on. It's been a year.
Because when you have to switch it over to the
Okay, so let's leave that as it is for right now. And let's just divide both sides by sine theta. So we have f of t1 plus negative f of t1 equals negative mass gravity over sine theta. Ah, okay. I see why. I see why. No, we're on the y right now. So up here, these two they can't cancel one another out on the y. They're not canceling one another out. The signs are opposite. So on the x, these things are in opposition. So let's look at our picture again. And I'll add one more color. I'll do it blue. So f of tx1 and f of tx2 cancel one another out. Do you see that from the picture? F of ty1 and y2 do not cancel one another out. They're both going in the same direction. So they're additives. Yeah. Now as far as the algebra, that's going to come to me at like midnight tonight. I'm going to wake up out of a dead sleep. That's why it's not the negative. But I don't have a better answer than that for you. Okay, so algebraically, this is now 2 f of t1 equals negative mg over sine theta. Can you solve at this point for f of t1? Sure you can. So f of t1 is equal to negative mg over 2 sine theta, which is really easy, but we kind of went through a proof to get there. You're still not okay with it?
Another question.
Okay.
Could we use the negative f of t so it was negative 2 f t2?
Negative
Instead
2.
of putting in our f of 1 so they didn't get it. Oh my God, these supposed to be-
It would still be,
The negatives would cancel, but we still have our 2.
no, I don't think.
We'd have negative
Let me run that whole thing after we do this. You may have a workaround, but I'm not going to say yes yet, because I'm thinking that it may end up being the same thing
I think it would be the same with that, just we wouldn't have a negative sign. So we'd be
to deal
dividing
with.
by negative 2,
Right.
so it would be positive.
Let me think about that. Okay, so f of t1 is equal to the negative of 10 kilograms times 9.81 meters per second squared divided by 2 times the sine of 40 degrees. Oops. Okay, so we have a raw answer of 76.3, etc. newtons. We have sig fig 76 newtons force of tension on each cable. Okay, now let me run the algebra with your suggestion.
Then we're going to have a negative because
Yeah, see, I thought it would end up being the same thing. So what I'm going to say is conceptually you can look at it and say, oh, well, the forces of tension on the y are not in opposition, and this is where your picture comes in.
so when it gets harder and we actually have an expression,
for
You-
the F of T's and that kind of stuff? Will it still work?
I don't remember a case where it didn't last year. And I remember
When we plug it back in.
for right now, yeah. And I'm going to come up with a better answer than that because I don't like that answer. I don't think it's a good answer. I don't think it's a good answer. But I'm trying to remember why. And I may end up cheating and going back to my old notebooks. Okay. This should allow you to do number 4 really easily. So go ahead and do number 4. And then when you get to number 5, I'll start giving hints. On number 4, where we have the gorilla hanging, that's where your 30 is. So I wanted to be able to draw that for you. And I'll record this for posterity. My mistake. So I used, for the force of tension X and force of tension Y, this angle, if this is 30, this angle is 60. Yeah. Well, you're using the angle that the angle that you're figuring from. Yes.
Okay.
You can if you flip that. So if you did it like.
Oh, my bad. I had your answer sheet.
That's okay. If you did 30 here, and you did your f of ty here, and your f of tx there, then that's 30. Then the y would be cosine of 30. See how that's different? So this angle, if this angle's 30, so's that. And if you're using this angle, then your f of ty is your cosine.
Okay, that's what I did.
Here, if you're using this angle, f of ty is your sine.